And quiet, please, and we'll start the quiz. Awesome. Close enough. AA. Silence, please. Give me an answer by 24. Give me an answer by 40. Not bad. Give me an answer by 25, please. Awesome. Okay, cool. Basically available systems are more tolerant of failures, but we'll see a little bit later on. The tricky part of that, 50-50 chance. More people got it right than got it wrong. Partition tolerance here, this one was, most people got this one right. So this is C. This is no set of failures less than total network failures allowed to cause the system to respond incorrectly. That is very, very strict on what it means to be partition tolerant, and we'll see that in a little bit more detail if we get time to it. And then CAT, this is the title of the reading. Consistency, availability, and partition tolerance. D is correct. So I'm going to cover a little bit of finishing up various topics that we've been covering at the application layer. And if I do have time, at the end of that, I will be going over distributed systems, which is it's a tricky topic. There's a really hard but really good 500 level class for the grad students, any undergrads who are like, please let me in to take. What we're going to do is just enough to be dangerous type stuff today. We're not going to be going into actually how to prove distributed systems correct or how to design them, because that's much, much trickier than it would sound at the outset. So let's see. First thing, there was a question about chunked encoding. Does anybody want me to explain that a bit more? Did that seem tricky? If you started looking at the assignment, what's up?
Well, I just have a question. So in chunk encoding, after the first chunk, there's a number. And then after the second chunk, there's a number.
Right.
What are those numbers?
So that, I think I have enough time to try and plow through this. I prepared some stuff. So the basic idea is that sometimes you don't necessarily know how much of a file you want to send to the other side. What's really, really important here is, so with chunked encoding, there's going to be the body of the response. So it's going to say something like, what is that transfer type? What's the transfer encoding? What's the header? Some header says chunked. It basically says you need to interpret the body of this. And we're going to have the headers of the response, and we're going to have the body of the response. We're going to have the headers, and we're going to have the body. And usually, especially in HTTP 1.0, when you are just doing a regular old connection close, response from a server, what you do is as soon as you have seen that you've seen the delimiter between the headers and the body, is you say, okay, now I'm just going to read bytes until the other side hangs up on me. And hanging up at this abstraction level is you can do a for chunk in whatever, you're going to receive headers. So when you're going to call receive on some socket, so we're going to do sock.receive and say we ask for 4,096 bytes. In Python, we're just going to get back here anything between 0 and 4,096 bytes total. We're going to get back some number of bytes. That's just going to be the return value of this. We're just going to get a string back out. Any value between 1 and 4,096 means one thing. It means a length string between 1 and 4,096 bytes means here's data that the other side sent to me. 0 bytes is a special thing that means the other side is done talking to you. This will only ever return, in this situation, a string of length 0 if the other side has said, okay, I'm done talking to you. So the easiest way to receive an HTTP response is to send your request, receive the headers, and then start receiving the body, and just keep receiving until you receive until you try to receive a certain number of bytes. This means up to 4,096 until you receive 0. Once you receive 0, you know that everything between the first byte you received there and the last byte is just the body of that thing. You can take exactly those bytes, throw them into a file, throw them out to standard out, whatever you're supposed to do. That is correct operation. If, however, we're told that it's a chunked encoding, it's basically, instead of all raw bytes, it's going to say some number of bytes, and then maybe a semicolon, and then maybe a bunch of garbage, and then a carriage return new line, and then it's going to give you exactly that many bytes. So the important part here is that rather than, it doesn't matter. You can put this 2 or 10 or 1 or 4,096 or a million. You can choose how many bytes you pull off that socket at a time. The operating system is going to give you the bytes that the other side wanted to give you in the order that they wanted. And they might give you 4,000, they might give you 200, they might give you 2,000. It's up to them, because all that matters at a conceptual level here is that we have a reliable in-order byte stream protocol. Whether it was in 1 packet or 2 packets or 10, doesn't matter. What matters is that we have these bytes in this order. So in this situation, if we get back, if it says there's going to be exactly 123 bytes, then that means that we can read exactly 123 bytes here. Maybe the first time we read, we only get 100, but we know we should never say consume out of this pipe, out of this socket, out of the socket that we have. We should never consume more than 123 bytes total. So if I call receive, so the next call to receive after I have read and parsed exactly these bytes out should be, I'm going to do mysock.receive of, what would be a good argument to put here for the number of bytes I want, up to the maximum number of bytes I want to expect. 123, right? So say I get something back here, I get 100 bytes out. So I get 100 bytes out of that return value. What should I probably put in my next call to receive? I'm going to do mysock.receive again, and just get data that I'm supposed to output to the user, or whatever have you. What should I put in there? Any guesses? Any guesses from anybody who hasn't guessed yet? One would be valid, right? One would be correct. Okay, out of, let's do this. A is 1, B is 100, C is 23, and D is 123. Answer by yourself what you think the correct argument to receive should be here in that specific situation. All right, give me an answer by yourself. All right, give me your answer by 30 seconds. All right. There's definitely no agreement. So discuss with your group and please agree. Did you forget your clicker? What's that? Are you just kicking it? Okay, cool.
Because the first line it's like, oh, the next data device. Then we receive the data, now we're asking, can we put it there again? And then look at the email. Well, like, what you received, you received 123. We received 123. Well, after that comes, oh, okay. Yeah, then you put 23. Yeah, yeah, put 23. So they didn't see the rest. They can receive at most. Oh, okay.
All right, come to some flavor of agreement by a minute 30, please. Minute 30. Remember, if your group wussed out because of the snowstorm, you can still get good points as long as you agree with yourself. Okay, we're still struggling on this one. So, the semantics of reading out of sockets, like reading and writing out of sockets. This is stuff we cover in 361, and this is pretty important when you're reading and writing files. In Unix, everything's a file, and so we kind of make network connections look like files just as much as we would any real file that we open off of the hard disk or whatever have you. So we get a lot of the same semantics of this API of how we're supposed to use it. So normally we could just say, I want this many bytes, and the operating system is just going to dole out that many bytes to you. There's never a reason for it to give you fewer than that many, because you're just reading off of a hard drive, whatever have you. There's some static file, you're reading it out, and you have a buffer in your program. You shove that much in. You made some buffer of 4,096 bytes. You shove things into it. It's very convenient. It works out that way. When we change what we're actually dealing with, we change the abstraction a little bit. So we are going to be getting very, very often, you're going to get less than, say, the number of bytes that you expect, because you're running some protocol, and maybe sometimes you don't know how many bytes to receive, right? If I'm asking for a file, I probably don't know how big it is. I don't know what's in it. I'm just going to wait for the other side to give me everything inside it. And so one way we can figure that out is we can say, okay, we're going to literally be told you need to expect 123 bytes of the data in the response from the other side. And if I've received 100 bytes here, then 3 of these are good, 1 of them is optimal, and 1 of them will almost certainly give you incorrect behavior and screw up your program if you were to try to use it when you try to program this protocol. So if I was told by the other side, by the server, that I should be expecting 123 bytes before the next chunk header, and I have consumed 100 of them, how many bytes are left within this individual chunk? 23. Yeah. That is a very, very hard story problem, but that's like a elementary school level story problem. We can do this, right? There's a lot of context involved. So if we've consumed 100 bytes, what's important here is that when we do receive, we're reading out of a buffer, and so we're given those bytes, and they will never come back from the operating system ever again. The operating system won't be able to say, oh, hey, or I as the application programmer can't say, oh, hey, you gave me those 4,096 bytes, but I actually lost them. Can you give me those again? They're going to say, no, like, I'm going to give you say read 1 or receive 1, you're going to get 1 byte. Operating system is going to forget about it forever. You say receive 1, you get another byte. Operating system is going to forget about it forever. So you consume these 100 bytes. The operating system has thrown them away. It will never care about them again. It can use that memory for something else. And then you know that you need to get 23 more because that's what the protocol told you, and that's what the server on the other side said about what is in this response. So if we were to consume, oh wait, there's 2 of them that are actually incorrect, super incorrect. So 100 and 123 would be super incorrect. 1 will still get us to what we want to get to. Question? Yeah. So at this level, so what's really important, that when we're at the application layer, packets don't exist. Like all that exists is bytes coming to our program via this call to receive. And even when we call send, even at that point, we're not sending packets. All we're sending or receiving at this point is bytes that we're telling the operating system, hey, deliver this chunk of bytes to the other side, or, hey, here are bytes which have been delivered by the other side. They could be 1 packet. They could be 1,000 packets all chunked together or all concatenated together, but we don't know, and the great part is we don't care. Yeah. Well, the uniqueness doesn't really make sense. Like if I wanted to send you a file that was like my favorite letter, and it was like A, etc., like it would be all the same bytes. Okay, so if we're thinking about things, so bytes, it's really, really good to be thinking in terms of bytes in a byte stream versus packets that are, coming off of a wire and being sent to the operating system, right? At this level, it's when we're dealing with TCP, when we're dealing with a reliable in-order byte stream, all we care about is some list of bytes, and that's just like what we see in Wireshark. Like it's a bunch of, 8-bit characters, like uppercase A, then uppercase A, then uppercase. It's whatever the application wants to send to me, and I could receive 1 or 2 or 10 or 100 or 1,000. They're all the bytes. And the important part, I think, was what you're asking is that maybe the other side was sending 1 packet at a time, and each of those 1 packets had 1 byte in it. This wouldn't really happen. This usually won't happen in the real world, but maybe it was saying, oh, I'm going to send you 1 packet with 1 byte, and this is the first byte, and then this is the second one, and this is the third one, and this is the fourth one. Maybe the other side sent the first one, it sent the second one, it got dropped, it sent the third one, and then it sent the second one again when it realized, oh, hey, I need to send that second one again. You, at the application layer, don't need to care about that. You will get out on your side the packets that were put in by the application layer in the order that they were sent, or the bytes in the order that they were sent. There won't be any holes, there won't be any repetitions, and it will end when the other side either gets unexpectedly disconnected or chooses to end the connection. Like, so you don't have to worry about the reliability of the channel. You don't have to worry about, oh, did the 2 packet, oh, the first one just got delayed, and then it got sent again. Like, oh, no, like, is this A the same one as this A? You don't have to worry about that at all. We'll worry about that next week, but we don't have to worry about it at this point. At this point, you can just consider that channel to be a magical, reliable byte stream that gives you exactly the bytes the other side sent, regardless of whether packets got dropped or whether they were tiny packets or big packets or whatever have you. Is this getting you? Good? Fantastic. Awesome. Thank you for asking that question. Okay, so of the 4 different ways that we can do this, if we were to ask for 1 byte at a time, it'd be like, yeah, that's kind of dumb. It's not good at a performance level, and you would also have to keep track of how many more bytes am I supposed to get here. I'd have to have some other way to keep track of that. Like, oh, get 1 byte, get 1 byte, get 1 byte. It's true, I could say, I could have some n that starts at 123 and I decrement it by 1 every time I get a new packet. But that's a terrible, terrible idea. It's a much better idea to say, okay, I know based on my protocol that I should be reading this many bytes, and I just read. What you can do, what you will do when you do your assignment, when you do this coding, the most important delineator is going to be between the headers and the body. There will be some \r, \n, \r, \n. Like that is going to be basically the magical symbol that means you've finished reading the headers. You can now parse them. And here, every byte that comes after that is the body. So everything before that is header. Everything after that is body. And an easy way to do this would be to receive some reasonable number of bytes and then parse through that and say, have I seen the end of the headers yet? If I have, then parse them. If I haven't, continue reading until I have found this string of bytes. And then I can start doing whatever it is I need to do. Maybe I need to do chunked encoding and receive via chunked. Maybe it's not chunked and I can just receive every single byte and throw that into my output buffer or whatever I need to do. But that's a decision that you need to make. If you were to read 100 in this situation, or 123 in this situation after you've received 100 bytes, why is that a bad idea? Yeah.
Middle of a reason for the next chunk.
Yeah, so you're going to have to either read that in and then parse through the bytes you got and say, okay, these bytes are now bytes I need to worry about later. Here's the bytes for the first chunk. Here's how I parse the chunk header and then get started moving forward. It's generally a good idea to just read in the number of bytes that you need, no more, no less. That's going to get you the best performance for what it is you're trying to do at this point, and it's also going to make your code as concise and understandable and readable as you would want it to be. Because if you read, say, 100 from here, it's completely possible that the other side sent its new 2, 3, 4, its new header of how many bytes to receive, and you've all of a sudden read past those 4 bytes, and now you've got to go back into that chunk and split it apart, deal with it. You don't want to do that. You just want to say, okay, I expect 123 bytes. I'm going to write a for loop that will consume no more and no less than 123 bytes. And then I'm going to read my next chunk header. And then one trick that we use over and over and over again is if you are at the end of it, reasonably certain the protocol is that you can just put a 0 here. That'll say, okay, this is the end of the chunked encoding. So that's probably the trickiest thing that you have to do on this assignment. And I would probably say it's not that tricky in the grand scheme of things. But yeah, if you have a question, you should definitely get started on this while you're holed up over tomorrow and the next day or whatever. You can't leave the house. You've got your assignment. You've got your laptop. You can have a good time. All right, that's chunk encoding. I went way over on that one. Okay, so I'm going to cover a little bit of DNS stuff. Yeah, a little bit of DNS stuff, a little bit of DHCs, a little bit of overlays, a little bit of distributed systems if we have time. The next thing I want to cover is, so at the end of class, the last time, I talked a little bit about authoritative name servers versus recursive name servers. I think this bears repeating because it's very, very important to the way that DNS gets deployed and your understanding of the concept that is DNS within the system that is the internet. So when we have our authoritative servers, again, remember, there is a limited number. I did this drawing before. I think I'm going to try and do it better. There's a limited number of domains, and there's an unlimited number of clients. This domain gets served to the entire world through this authoritative name server. And it has authority functionally within the system because the server above it within the hierarchy said, go talk to this specific server. Go talk to this specific IP address. They are the ones that are in charge of resolving chris.com or all of edu or cs.uic.edu. So some limited number of domains get served to all clients on the entire internet. In contrast to that, we have local DNS servers, where local DNS servers have some limited number of clients, again, unless they're like 8888, and they are supposed to serve all domains in the entire world. Now you can have your own computer do this. Like it's it'll take a half a dozen keystrokes or whatever in Linux to say, oh, I want to run my own recursive caching DNS server, and it will do the caching, it'll do the lookups, and you're the only one that's doing that. That server will then be going out to the hierarchical DNS system and asking for every single thing that your computer wants to look at. But these recursive, like local, and the right thing, local, like let's say recursive caching DNS server. That's definitely the most accurate name for it. And then these are authoritative servers. And that is the most concise way that I can think of to talk about these two different flavors. There's nothing about the spec itself that says you can't have one server that listens on port 53 and does both recursive lookups for clients and authoritative answers for the entire world. It's not a good idea. These are serving two very, very different needs. Like this is based on some domain name needs this to exist on the internet. It's very abstract. Like where it is doesn't really matter as long as it does its service. The recursive name server is mostly a performance thing. It makes everything a little bit more resilient. It makes everything a little bit more efficient. Makes everything a little bit faster. It's nice, but it's not an absolutely necessary thing. Every single client in the entire world is completely allowed to do the recursive name lookup all by themselves all the time. So there's one important thing I really want to cover, and unfortunately it's the worst thing about the book that we have. In general, I really, really like the book that we have for this class, but it has this ridiculous, super confusing component to it about authoritative DNS servers and the difference between recursive DNS servers and iterative DNS servers. It has some conceptual point, but it is not reflected at all in the way that the real world works. So if there's some host called Allspice and it wants the IP address for this Gaia server, in an iterative query, it's going to look that name up all by itself. It's going to look up one, it's going to look up another one, it's going to look up another one. What that ends up looking like is, let's do this. Yeah, so in an iterative query, that's basically one individual DNS client contacting the root. So if I have my DNS client, and I contact the root, I contact the edu domain, I contact the UMass domain, etc., all the way through. So this is iterative. One client is going to go talk to one server, and then it's going to go talk to another server, and it's going to go talk to another server, etc. That is a not, in and of itself, this is a non-recursive query. This is an iterative query. Now, the way that DNS works, when you do a DNS lookup, you have an option to give for your DNS query to either request recursion or not. The way that we use recursive caching name servers is to either choose this bit or we don't choose this bit. If we don't choose this bit, let's pull this up. Recursion, yeah, so we set this recursion desired bit or not. If we don't set a recursion bit, what we're basically saying is we are a client and we're pretty sure that you're the authoritative server. So all we want you to do is we say, hey, if you own this domain, give me the answer for it. But if you don't own the domain, don't go out there and figure the answer out for me. And that's what you do when you are a regular old DNS client. You are not going to ask for recursion as a DNS client, which does the DNS lookup protocol, the one that goes through the entire hierarchy, walks down from the root. However, most DNS resolvers are what are called stub resolvers. The ones that you have in your phone and on your operating system by default are stub resolvers. What they're going to do is they're going to say, hey, I don't have the time to go look these names up from the root, then to edu, then to UMass, etc. All I want is someone else to do that lookup for me. And what that lookup is called recursion. So if we're going to do a resolution in a recursive manner, it will look more like, it will look like the first two sections of this lookup example, where I, as the requesting host, say, hey, I'm going to ask with the recursion desired bit set this local DNS server. This local DNS server is one of these kinds, a local caching recursive name server. It knows how to do the lookup through the rest of the DNS hierarchy, and it does lookup for you. But the most important part, based on that is super confusing in the book, is that this part here is still iterative. There's this horrendous drawing in the book, and I don't think I have it in these slides. Yeah, I don't have it in these slides, but there's this horrendous drawing in the book that looks a lot like this one, and it says, here's what a recursive DNS lookup looks like. And it's your client contacting one server, that server contacting the root contacting the TLD contacting the CS.UMass server, and then that response coming all the way back. That is what would happen if they all set the recursion desired bit, and really importantly, all of those servers were willing to do recursive lookups on behalf of some other random internet host that they'd never heard of before. So, in reality, this server and this server and this server do not advertise that they are willing to do recursive lookups for you. And so you have to go through them and ask them, hey, give me information that you're authoritative for, receive that back, and then continue the iterative steps. But that's the big difference between iterative, which is I'm going to do the protocol myself, and recursive, which is I'm going to ask someone else to do the protocol for me. In practice, I am not aware of. I guess there are situations. So if you're at home and you're on your local Comcast router, you are going to have your own laptop, and you have been given a DNS server by your DHCP server in your local gateway, your local home Wi-Fi router, and it said, okay, just look up through me. I will advertise recursion to you. You will do this recursive lookup for me, or you will ask me for that recursive lookup. I'll do it for you and give you the answer back. In actuality, your Wi-Fi router will then go and ask the Comcast router, or whatever one it's configured with by default, to go ask, hey, you are the actual recursive name server. Go do this for me. So DNS was engineered with this option to just delegate to one server. That server's like, well, I don't want to do it. I'm going to delegate it to this other server. This other server can say, oh, well, my job is to do these iterative lookups and then return them back to you. That is the way that things work, but there will never be a reality that I'm aware of or that I would bet existed where you can just have recursion go all the way through that hierarchy and have it give you an answer back. This is tricky stuff, and the book is amazing otherwise, but this is one concept that I feel like it stumbles on. So hopefully I didn't confuse you more. I am recording this, so if you want to watch it again, I would highly suggest doing so. Okay, one other little bit about caching. So once any of these name servers, especially the local recursive name servers, learn a mapping, they will keep it in their cache. They'll keep it in their cache until its TTL expires. And the one really important thing about these caching servers is that they will, when they advertise a cached response, or even any response, not even a cached one, but a direct one that one of these local recursive caching DNS servers does, they will advertise it with one bit not set, and that's the authoritative bit. So let's do dig at 8.8.8.8 edu. So it is going to say, Here's the start of this authority, whether this is authoritative or not. One of these bits is this answer authoritative? The answer is usually going to be no. This is not an authoritative answer. This is an answer that I just have cache that I'm willing to give back to you. Because I am not in charge of that server. If a DNS server is giving you a response back, and it's not in charge of that domain, if it's not the one that is authoritative for that domain, it will not set the authoritative bit. So what that basically means in addition is that this is some value that this was looked up for you, and it started with some TTL. When you get the TTL from the authoritative server, that's when you start counting down. What happens in the background at these authoritative name servers is that there's some file. There's some file that says, I choose to let my domain mappings last for 900 seconds, and here is one of the mappings. Like dns.google.com goes to 8888 or something like that. And if somebody looks up at an authoritative server, hey, I want you to tell me what's the mapping for dns.google.com, and the authoritative server says it's 8888, and the TTL is 900. If I wait for 5 seconds, I go back to that same authoritative server, and I ask the same question, will the TTL have decremented to 895, or will it be 900? What'd your guess be? 50-50 chance of being right. Okay, now I'm curious. This is important stuff. I'm belaboring these points. So let's see. So step 1 is look up name X at server Y. Step 2 is wait 5 seconds. Receive TTL 100. And then step 2 is wait 5 seconds. And then step 3 is repeat step 1. And our answers are and now what we want to know is what's the TTL of that response. And your answers are A, it can be 100, or B, it's 95. Give me an answer all by yourself in the next 10 seconds. Oh, I'm already. Here we go. Next 10 seconds, next 10 seconds. Close enough. Okay. All right. Also, Administrivia, if you run out of the room and come back and you miss like one question, it's not going to affect your participation grade. There's a lower bound of you need to hit a certain number of questions, then you're fine for the day. So if you miss 1, miss 2, don't worry about it. But if you miss half of them, worry. Okay, so the group is split. One person said C, but again, we're not worried about correct answers. We're just worried about answering. Go ahead and discuss with your group what you think the right answer should be. This is an authoritative server. It has some configuration file set by the administrator. It is the source of truth for that domain name. Yo. Local Comcast routers, like remember like the first, second day I was like, oh, a home router actually has these like 17 different things in it. Like DNS server, like local caching DNS server is one of those things. It does, but there's nothing about the internet or the protocol or the requirements that it has to. Like that's just the way that those things get deployed. There's no, a router is just a thing which moves packets between 2 places. It doesn't have to do these extra services like DNS or DHCP or like local web interface, any of that stuff. So in general, routers do not have to, and 99% of the routers on the internet don't. Okay, give me an answer. Please agree by 1 minute and 28 seconds. Oh, my Poor computer. Okay, we are still not really agreeing with each other. I guess your own group probably agreed, presumably, because you want your points. But yeah, so this lookup, this name, if I'm authoritative for this, all truth about this domain name flows from my server. And my server is going to get that truth from some configuration file. So if my configuration file says when somebody comes to me and says, tell me this lookup or tell me this name, I get to tell them what the TTL should be. And so I get to tell them that it's going to, if I say it should be 100, then 100 is the correct answer. That, by the way, in this situation, that is the correct answer. So if I have said in my configuration file for this authoritative server, I say this name has this TTL, this name has this TTL. Like, yeah, I could write a DNS server where I decremented it like every minute or something, but the way that everything works in the world is that you set some static number and you say, when a new client comes in and wants to know about this name, give it this TTL. So we know that if this server, say, goes down at some point in time, we can just say, okay, we can guarantee that if that server went down within 100 seconds, all of those mappings that went out into the world will no longer be valid and we're good. But the source of truth for these mappings, this is the important part, is that file that's on that authoritative server. Now, in juxtaposition, if you were to do the same exact thing, but that server that you're looking it up at is your local caching DNS server, your local recursive caching DNS server, what do you think would happen in the same exact situation? Would it be 95 after 5 seconds if you looked it up again, or would it be 100? Give me an answer by yourself. And give it to me by the time that thing says 10 seconds. Okay. Still not doing that great. Okay, discuss with your group. And please ask questions if you have them. This question is, in a situation where I look up a name at my local recursive caching DNS server, I get back some response that has TTL 100 seconds. I wait 5 seconds, then I ask at my local recursive caching DNS server the same exact question. Will I get an answer with 95 seconds of TTL or 100 seconds of TTL? All right, come to some form of agreement by a minute 7. Okay, we need to duke this out. Let's walk through this. If we have we have a caching DNS server. Let me put this slide up. So caching and the TTL are this very, very important thing. We want to cache because it will allow us to minimize the load on the entire system. If a bunch of people that use this local recursive caching DNS server want to know the same name, then this one should just save it. It should save it so as soon as some other client comes in, it can immediately give the response back. That's what we want to happen. That is much, much better performance than this local recursive caching DNS server going out and saying, oh, hey, what's your answer? Okay, cool, got it. Oh, what's your answer? Okay, cool, got it. Oh, hey, what's your answer? Okay, cool, got it. And then I get to respond to the client. That is way, way, way slower than, oh, I saved it. I was told by the server, who is a source of all truth for this name, that I can save this for 100 seconds. Is this server the source of all truth for that name in the internet? No, all this server does is makes things faster. It's not in charge of anything except making your internet faster. It's not in charge of Google.com or Chris.com or whatever example we're talking about, all it's doing is taking an answer it heard from somebody else that it is not in charge of and then handing it to you. And part of that answer is a deadline which says you're only allowed to hand this answer out until 100 seconds have passed. So that's what a recursive DNS server is allowed. A non-authoritative server is allowed to do. A caching DNS server is allowed to do. And when you are using DNS lookups locally, you are going to be doing effectively the same thing. You're going to say, okay, I looked up google.com to make the first HTTP request, and I made the TCP connection, and all of a sudden I realized, oh, I need to make another TCP connection to that same server, and your operating system will say, oh, do I have a mapping for google.com? Has it expired yet? If no, immediately make that connection. If yes, go ahead and look up google.com because it might have changed in the meantime. But it's going to be counting that down. So, with that explanation in mind, let's try to answer that question just one more time about doing this hypothetical situation at a local recursive caching DNS server. Will the second lookup have TTL 95 or will the second lookup have TTL 100? Answer that one for me. Give me an answer by 13 seconds. Okay. At some point in the not too distant past, I thought I was a decent teacher. But I'm not. No, this is my fault, right? Either you're just hitting A so that you agree with everybody and you're not really paying attention, or I am not getting this across. So the correct answer here, when we're talking about this local non-authoritative server, is that after 5 seconds have passed, it cannot tell the rest of the world, hey, I know that this thing is still valid for another 100 seconds. It cannot continue saying, oh, this is still valid for 100 seconds. This is still valid for 100 seconds. Like 5 minutes later, yeah, this is still valid for 100 seconds. It can't do that because it's not the source of truth there. So when you are this caching server, and you can see this happen. If I do a lookup in my terminal, if I do host www.usc.edu, I'm going to get, oh, no, let's do dig this. So when I look this up, the first time I look that up, from here, I get 900 seconds. See that there's 900 seconds on that lookup coming from the server that I asked. Now if I look it up again, gosh darn it, this is saying 900. Let's do dig at. So the UIC recursive name server is not doing what it should be doing because it's the local one. Let's do this. All right, so that one is saying 813 seconds. So that's a better situation. When you're on that same campus, they do the one thing that I told them that they probably shouldn't do is just return the same full length TTL. Now if I look it up again, I'm getting wildly different TTLs. What the heck is going on here? Okay, maybe I'm not a bad teacher. Maybe I'm just going crazy. That column is supposed to be the TTL of the response. I have no idea whatsoever why it's jumping all over the place. I mean, I'm asking the same server. There could be multiple caches. Maybe I'm hitting different caches. What is a decent? Is this one? That's not a DNS server. Question.
So it will only update after the TTL is expired, or will it actually try to look up before?
So there's two situations that could happen. One is these are LRU caches or whatever. There's some cache with a finite amount of space. So there's so many people looking up so many things that the amount of memory it has for its cached responses fills up. It'll just eject one of them, just like we know about caching everywhere else. And it'll say, oh, I don't have this in my cache. I'll look it up again. So that's one reason that it could get ejected. The other reason is that it passed its TTL. Good question. Doesn't get us any closer on the mystery of the like crazy TTLs. Oh man, what's another? So yeah, we're asking this server, and it just doesn't want to update the TTL. If you do this experiment at home, it might work better. And I think, so the thing with the Google DNS server is that maybe it doesn't, I literally can't give an answer for why it's giving us completely randomized TTLs. I got nothing. This made sense. I have done this demo before, and it has worked just the way that I expected to, but apparently not today. Do you have a question? Yeah. Oh, okay. Yeah, there are some. If you are not authoritative for a domain, and that one keeps saying 7200. Question?
Yeah, why are we in, what exactly are we looking at?
We are looking at the response of a. That's not inappropriate. So I'm doing a DNS request to this specific name server for this specific name. There's a whole bunch of information. This is basically a very fancy version of what you'd see in Wireshark. It's just a lot easier to open up your terminal and do this. This is just a DNS Swiss Army knife. It's going to have a whole bunch of information about what headers are in that DNS packet. The DNS packet itself is a packed binary format. A lot of this information that we're seeing here is like human readable versions of like very, very terse data. Like there's going to be a 2-byte field that's the DNS query ID, and there's going to be a 1-byte field that has a whole bunch of flags in it. This is just an easier human readable version of the DNS packet protocol, packet format. So we see what question we asked. We want to know the A record of an internet name with an A record of this name. So the key I'm looking up is www.uic.edu. From this response that I got back from this server, I get these answers. These answers say the name you looked up has a 900-second TTL. It's an internet name. It's a CNAME, which is the canonical name, which basically means it's the pointer that goes to this other name. And because it knows that's what we want to look up, and it has that mapping, it says, oh, that pointer that you asked about, or that you want to know about, obviously, because you need to make an IP connection, has an A record, because that's what you're asking for, of this IP address. So we ask, what's www.uic.edu? We get back 128.248.155.15. If I run the host program, I get a very, very simple version of that. So that's the same exact thing, but like only the semantically important information rather than all this like semantic debugging output of here's everything that came back in that packet is here. This is what do you need to know about the mapping between this DNS host name and the IP address that it resolves to. That's what you get out of this one versus what you get out of DIG, which is much more Swiss Army knife. It's got lots of options. Does that get you closer to your answer?
Well, yes, but it's a little bit more specific than that. Which TTL response time are we looking for?
Oh, well, I totally overshot. You should interrupt me next time. This is the TTL.
Right.
What should be happening? Let's figure this out. Let's figure out which server, who is authoritative for www.uic.edu. I can do dig ns www.uic.edu, and I will be told who is authoritative. The start of authority for cc.uic.edu, at least, is, let's do this one. So, UIC, DNS, blah, whatever, is authoritative for this zone, uic.edu. So, the hierarchical DNS system says this server is allowed to give me real, honest-to-goodness answers for things within uic.edu. And is that what I'm actually looking up? Yes, I am looking up this. So UIC thinks it's a great idea to both use its recursive resolver. So this recursive resolver is the one that we were given by DHCP when my laptop joined UIC Wi-Fi. It said, hey, I know that you're going to want to look up DNS hostname. Here is the IP address that you should ask. 99 times out of 100, that is not going to be an authoritative name server at all. It's going to be a server that's just in charge of doing this one thing. UIC decides that it's a good idea to have this server both serve recursive queries locally as well as be authoritative for those names. So this UIC-dns3.uic.edu is a name server which is in charge of uic.edu. It's allowed to return authoritative answers for that zone, that anything within uic.edu, and you can trust that that's going to be true for the next 900 seconds without asking again. And then when we come down here to the additional section, we say, oh, UIC DNS3 for the next 900 seconds, we can trust that it has this IP address without going back and looking. So yeah, we've been asking the authoritative server. So this part makes sense. It's kind of dumb to set it up this way, and you'll see that this iStation.uiuc, that one was probably counting down. That's not some nice big number. Yeah, so this one's counting down in a way which is consistent with my understanding of reality. Yeah, so if I wait 3, 4, 5, that's going to count down. Right. The server that we are asking is authoritative for uic.edu. It is not authoritative for uiuc.edu, and thus it cannot return to us, this is always what this true answer is. It has this in its cache, and it knows that it has some deadline after which it can't send it to anybody, and it knows it has to decrease that amount based on the amount of time that has passed. So that will give us question. Yeah, there's a very good chance. So a bunch of DNS servers behind a load balancer, this is above what we need for this. So you probably wouldn't do that on a DNS server because you're incurring way more effort than you would need otherwise. What you usually would do is you'd put it behind multicast, like a multi-homed IP, where that IP lives in different networks. We'll see when we get to the network level of the class, we say, oh, 8888 lives in this network. It also lives in this network, and we're going to rely on the routing algorithm to say, oh, this is the closest version of that server. So lots of different places in the world will successfully respond to that IP address 8888. That's called multi-homing the IP. So for some reason, one path goes this way, one path goes that way. It could be living behind a load balancer. I wouldn't expect it, but it's completely possible. But yeah, good point. Okay. Yes. At least we're... Oh, 4. Yeah, 4. So the why we have more than one authoritative server is just that if one of them goes down, remember that DNS is critical infrastructure. It's critical. The root is critical for everything we do on the internet, because any DNS name you look up has to start from the root of the DNS hierarchy. But anything that you ever want to do that has to do with looking up uic.edu, which means sending email to uic.edu, going to the UIC website, going to, logging into your UIC Gmail, requires that names under this domain get looked up successfully. So I would not want to trust that to just one server, and lots of places don't want to trust it to just 2 or just 3. So UIC chooses that we're going to have 4 different servers that hopefully are run in different ways, they're in different places. Like maybe one of these is actually on UIUC campus. That's actually very believable, seeing as one of them has a UIUC domain name. We just say, okay, just in case these other domains, these other servers out there on the internet blow up, people will still be able to look up what they need to and access it. Because what's interesting is that if these servers, if you looked up these servers, if you looked up www.uic.edu, and all 4 of these servers just got blown off the face of the earth, for the next 900 seconds, you wouldn't really notice anything. Everything would still work fine, as long as the DNS server and the web server weren't running on the same machine, or they weren't blown up in the same, crazy hypothetical situation. So you only really need DNS to make that initial connection. All you need to do is look up what you're trying to find, then you find it, then you're like, okay, now I'm off to the races. I don't need to worry about DNS until I need to look up a new domain name, which means I'm going to make a new connection, or I lost my connection, I need to make a new one, whatever have you. So we don't worry about, like, DNS is relatively low overhead because you just look it up at the very beginning of some communication, then you do all the stuff you need to do, and then you're done. So you absolutely positively need it running at the very beginning. So that's why we have 4. Again, maybe I overshot it. Yes?
Do the port authority servers, do they have the same information or they have redundancy?
Yes, it's 100% redundancy. Maybe one server doesn't get updated as fast as the other ones. That would possibly be some incorrect operation. But as long as it's being run correctly, yes, they all have a copy of the same exact file. It gets updated probably within seconds of each other when the administrator decides I need to add a new name to the DNS. They're purely for redundancy among the different servers, because they're all supposed to be able to answer for that domain, and it'd be weird for us to answer different names if we looked it up from different servers. At the authoritative level, you can ask any of these 4, and you can just pick randomly among them whenever you get this packet back that says, oh, here's who you should ask if you want to know this answer. You just pick randomly from one of them, and you're good to go. But all are going to have the same answer. So it'll be like a little bit of load balancing. Like if everyone randomly chooses among those 4, then each of them will get 1/4 of the load. That's kind of nice. And they're for redundancy as well. Good question. Okay, important thing that I want to cover about caching is that sometimes, so just because we have this TTL does not mean that we are guaranteed that it is going to be the correct answer. It could be out of date, right? Like we set this TTL to 900, and then at some point in time, I'm going to want to change it from one thing to another. And everyone that had looked it up and still has that TTL cached, the website's not going to load correctly. I've moved it from one server to another, and all of a sudden, it's not responding on the old IP address. The cached entries may be out of date. I think if you do like Shift F5 or Shift Reload, like Shift Command R on the Mac, it'll force looking up the DNS again. But this is one of those weird things where there's no really hard and fast way to say, no, I really want a new DNS mapping. I want you to go back to the server, because there's no control over that, especially if you're using a local recursive caching DNS server. So we do this for performance reasons. We do our caching for performance reasons and for reliability reasons. But it's not perfect. Sometimes we change the mappings. All right. This stuff I don't want to cover. Okay, so when we were in the 11 minutes I have left, any more DNS questions? DNS is like one of the hardest, third hardest concept to cover in class, and also one of the most important. Awesome. Okay, so when we were talking a little bit about BitTorrent, in the olden days, when you wanted to use peer-to-peer file sharing, when you wanted to use regular old BitTorrent 1.0, what you would end up doing is you would have a server called the tracker, and the tracker would list, here's host 1, the tracker is going to say, here's host 1, here's host 2, here's host 3, here's host 4, and everyone that's within the swarm for a specific file will go up to that tracker and say, hey tracker, I'm here, I'm participating on this Ubuntu ISO. Just let anybody else know that they can download it from me if they want to. And so then the tracker will say, okay, great, thanks a lot for that information. Anybody that comes along, I will give them your name along with the 700 other IP addresses that want to help distribute this file. Now, that is a single point of failure, and it's a single point of failure both technically and then also administratively. Like if you want to stop file sharing, you don't have to go to every single cable internet customer. You just go to that tracker and you say, nope, I do not want you to share that Ubuntu ISO because that is obviously copyright infringement. So what's really cool is that we can solve this problem to a certain extent with distributed hash tables, with a trackerless peer-to-peer file sharing. We can do, and we're going to do this via a distributed hash table. So the problem we end up with is basically we want to have what looks like a key value store where the key is some file I want and the value is the IP addresses of the hosts which are participating in distributing this file. This is what we want. But it doesn't make sense for every single client that's participating to all keep this database because A, it's probably going to get really big because there's lots of different files that people want to share, and the IP addresses, that's going to be a pretty big list of IP addresses, and it's going to change really, really often because there's lots and lots of people. They'll be like, oh, I'm going to download this file. I'm going to download it. I'm going to download it. As soon as it goes green, bam, done, delete it, right? So that these IPs are coming and going very, very often. You'd have to be updating this key value store all the time, constantly. And if you wanted to keep it consistent among all of those different hosts, that's going to be a bad time. It's just not going to work in any reasonable semblance of acceptable performance. So what we can do instead is we can put this information into a distributed hash table. So if we go to our hash table, so remember, who remembers hash tables? I'm looking because it's like if you don't, we're going to have words. Hash tables are super, super important, even more so in Python because they basically underlie almost all the data structures you're going to use on a daily basis. What we have is we have some limited amount of space that we're going to store every single thing that we would ever care about, and we're going to store it based on its hash. So I have some really, really long thing, like my 4 gigabyte or whatever, like 800 megabyte Ubuntu ISO, and I'm going to run it through some hash function, and no matter whether it's 1 byte long or 800 million bytes long, I'm going to get out some fixed length description of it. In our traditional hash table, you say, oh, we're going to have like a 4096 bucket hash table. And so we're going to have these 4096 different buckets. We're going to hash it down to something that maps into that 4096 value space. We're going to say, oh, this thing goes into this one hash bucket, right? And we say, okay, great. I'm going to store some fixed number of things in this data structure, and the lookup is 01 as long as I don't fill up the data structure. Pretty great. And the size of it is going to be very important, right? What we're trying to do is keep our occupancy, I think, around or below 50% usually, and then we want to grow it. There's all that stuff, but that is a non-distributed hash table. We're going to have our hash function that brings us down to something. What's important here is that in hashes that we use to keep like file integrity, these are really, 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 really long hashes, right? Like 2 to the 256 different potential values, which is really, really short, right? You just have a 256-bit value. That's going to be what the file hashes down to. And you could think about that as a place in a humongous, gigantic hash table, but it wouldn't make sense to make an actual hash table that has 2 to the 256 different actual buckets in it. We have never and will never manufacture enough memory in the existence of the human race to make a hash table that big. That's just true. But we can say, let's cheat. Rather than creating this actual hash table that's actually that gigantic, we're just going to use that to bootstrap a hash table that is distributed. All right, I got 5 minutes. Sweet. So I am going to do this thing. So I'm going to say I'm going to take some file of some arbitrary length, and I'm going to hash it down. I'm going to say I'm going to hash it with SHA-2, a nice cryptographic hash function. I believe I get 256 bits out of this, but I don't quite remember. So I'm going to get 256 bits out of this hash function. And I'm going to say, okay, that is the address within this 256-bit space where I want to store this value. Now, in a normal hash table, every single bucket gets like an area in memory, right? Every single bucket is an offset into an array. But in this world, we're never ever going to have 2 to the 256 different buckets. We're going to say, let's just say that we got 4 different clients participating in this hash table. And we're going to say, we'll put one here, we're going to put one here, we'll put one here, we're going to put one here. What we're going to do is we're going to say, okay, somewhere between 0 and 2 to the 256, this is just some gigantic space. This is a gigantic address space that will never, ever, ever be filled, not even close. So we're going to say, no, these are different values. Maybe this one, actually, let's use slightly more understandable numbers. So we're just going to talk about this as 256, right? So let's pretend we instead have a 256 size hash function. It hashes down into 256 different values. And I'm going to have 4 different clients participating in this distributed hash table. And this one is going to be at like 7. This one's at like 70. This one's at like 80. And this one's at like 200. So all of these clients, they get a address within this distributed hash table. And we will say, okay, when I want to store any value, if I want to store any value in this distributed hash table, I'm going to hash the value down to what it's supposed to be hashed to. And I am going to go and store it at the client who has the smallest address larger than that value mod 256. So if I take some value and I hash it down to some value and I hash it out and it hashes down to 100, I'm going to store it at this client because this client has the address that is larger but smaller than anything else. This is the successor to the value that's at 100. So I know anyone else that's participating here can say, okay, as long as I know who's participating, I will just know who's supposed to be in charge of that. Something hashes down to 60, I ask this one. Something hashes down to 0, I ask this one. Something hashes down to 240, I ask this one. Largest one that's smaller than it, mod 256, right? The next one in that space is this client. So this allows me to store a hash table among different clients. So the first cool trick we're going to do here is to assign these addresses, right? When I put this up here on the board, I just made it up. I was just like, here's a number, here's a number, here's a number. What's nice is that if we're using one specific hash function and you have something that is your identifier, like say your IP address and port that you use to participate, you'll say, okay, well, I'm just going to say my address is the hash of my IP and port. That's my address within this space. And the neat thing there becomes both the clients participating and the content that you're looking for all hash down into this same exact space. And we're only going to be looking it up based on the number of clients involved. And maybe we'll store hundreds or thousands or even hundreds of thousands of things, but we don't need to go into some world where we create 2 to the 256 different array values because we're never going to be able to fill that much space at all. This will let us split that hash table up. We're still going to fundamentally be able to store whatever we want. We choose where it gets stored, and then the next thing that we have to figure out, which we will cover on Tuesday if we aren't all still snowed in, is how we actually go and find that. Because I haven't actually told you how do you find these individual clients. And it sounds easy when there's 4 of them, but if there's like 400,000 and they're all joining and leaving, it gets a little trickier. But we have ways to do that. Drive, ride, or walk safely, and I will see you all on Tuesday.